When two objects interact, the blank momentum before the interaction equals what goes in that blank? When two objects interact, the blank momentum before the interaction equals it's the total momentum. The total momentum that goes in, the total momentum before the interaction equals the total momentum after. And that's why the momentum is so useful. The total momentum before an interaction equals the total momentum after. So one might lose momentum, the other might gain momentum, but whatever the one lost, the other one gained. It's like a hockey game. You're watching a hockey game. Do you have this sheet? Yeah, good. You have the sheet. So you might see a hockey check. Oh boy, the big hockey player checked the little hockey player. Yeah, go. Anybody else need this? Because we spend an audience going to go get it. The total momentum before the interaction equals the total momentum after. Momentum is conserved. It's not lost. It's exchanged. The conservation of momentum comes from, which one of Newton's law does this come from? Yes, the third law. The third law. And I developed this already, but now I'll develop it slowly. If what Newton said is the force that object A exerts on B is the same force of B on A. So let's change this to the force of A on B is equal but opposite the force of B on A. Okay? So we know that force is M delta V over T. Delta T equals negative M delta V over delta T. And when two things interact, the contact time is the same, so this crosses out. So whatever momentum the one object gains, the other object loses. The momentum that one object gains is the momentum the other object loses. Let's take a look at here's a pretty simple situation. You've got one object with one mass and one velocity. So its total momentum, it's a single object with one mass and one velocity, piece of cake. This total momentum is, we'll call it this direction positive. So it's 10 kilogram meters per second because we multiplied a kilogram times meters per second. Now you have two objects, one slow object, one fast. What's the total momentum? Momentum, the first would just be 4 kilogram meters per second. This one is 9 kilogram meters per second, and the total would be 13 kilogram. Wow, great question. So impulse is the force and the contact time. So really it could have a unit of this. But since F times T equals M delta V, it's also allowed to have this unit as well. Yeah, it could be both. All righty. So let's take a look. Now, here are two objects headed towards each other, and they look like they're ready to crash. Let's get the momentum of each. Well, 4 times 1 is simply 4 kilogram meters per second. Now, the next one, we have to be a little careful about this next one. You might say, what do you mean you have to be careful? 3 times 3 is 9. Yes. It's negative 9. Because you can call right positive if you want, but you got to call then call left negative. You have no choice. So we can see these two objects headed towards each other. Their total momentum is negative 5 kilogram per second. Right. So yeah, I did. So well, because they're both going in the same direction. Yeah, opposite. So negative 9 plus 4 is negative 5. Well, I'm not subtracting. I'm still adding because 4 plus negative 9 is negative 5.
So you add no matter what.
Yeah, I always add. That's what total means. Yep. Okay, now two objects. What do you think the first one is? Be careful. This is obviously 15, but is it negative or positive?
Negative.
Yeah, the convention is right. People use this right as next. So negative 15 kilogram meters per second. This would be positive. Following the convention, kilogram meters per second squared. The total would be 0. That's really weird. They totally have no. Yeah, vectorially, their total momentum is 0. It's kind of odd, right? How could they have? Well, because they're yeah. That's the convention. But whatever you establish, that's the convention. If you could go against the convention, you still get negative, wouldn't you? If you said I'm going to call left positive, I'm going to go against the convention. You and I would still get the same answer. That's the vector addition, because momentum's a vector. Okay. Now let's take a look over here. Inelastic collisions. Objects attach after collision. Inelastic collisions. Objects attach after collision. Objects attach after collision. All righty. Now don't worry about this kinetic energy. We're just going to get rid of this kinetic energy. All this kinetic energy stuff we'll just ignore. objects attach after collision. So ignore all that kinetic energy stuff. All right, this one is going in the positive direction, so it's 18 kilogram meters per second, positive. Don't worry about that. And then after this, oh, what's the momentum of this guy right here? What's this momentum? P is how much? 0. It's not moving. Has no momentum at all. So the total momentum only comes from the moving object. The non-moving object doesn't. Now, the law of conservation of momentum says the total momentum before equals the total momentum after. So this has to be 18 kilogram meters per second. The total momentum before has to equal the total momentum after. Now, what is these combined? Now, 6 and 3 combine to make one thing that's 9, right? The combined mass is 9. Now it's just one thing of 9. What must its velocity be, these two combined masses? 2, yeah. 2 meters per second. On what basis? Because only 9 times 2 is 18. And so what will happen, these combined masses will go slower, which kind of makes sense, doesn't it? They collide, they attach, and this combined object will have 2 meters per second because let's write over here, P before, the law of the universe says equals P after. And we always add them up, never subtract, we always add them, assigning the positives and the negatives. So good, simple. So now look at this. You can actually predict what happens if a 6 kilogram object is moving in 3 seconds, hits a 3 that's at rest. You can predict that those two combined masses will have a velocity of 2 meters per second based upon the law of conservation of momentum. Now let's try this one over here. Why don't you do this one? Check that one out. Do that yourself. So ignore the kinetic energy question. Just kind of ignore it. Scribble it out if you'd like. So each one has a positive momentum. It looks like the guy in the back, he's faster. He's going to catch up and hit that other guy. And they're going to combine and make an inelastic collision. It means they join and become one thing. So you're doing okay? What did you find the momentum of each? We're going to call the rank positive. That's a good convention. We'll call them both going at a positive velocity with a positive. So what do you say? Yes?
5 meters per second.
That's the ultimate answer. Let's go piece by piece. What was the total momentum before?
40 kilograms.
Well, actually, isn't it just?
I think it's 6. Oh, isn't it? No.
I'm sorry. We're doing this one up here. My bad. We did this one.
No.
We did. Now we're doing this, right? 6 here. So this would be 25 plus 9, isn't it? Isn't it 34?
Oh my gosh.
34, right?
Yeah.
Now did I get that right? 25. You're not beautiful. And then you have one body, but with a single mass. Let's write this of 8 kilograms. And what's its velocity? Well, we know the total momentum. Newton would tell us the total momentum after this carbon would, of course, be. It was 34 kilogram meters per second. Yeah, it was. So it's the before equals after. That's called the conservation of momentum. Whatever is before equals after. And let me see if I can dig out my answer sheet and see what you got. Yes, 4.25. Now, of course, the values that they gave us were only one significant digit. It's kind of ridiculous, but let me check my 4.25 meters per second. Let's ignore the fact that we were only given one significant digit. We'll say 4.25 meters per second. You're good.
It's 34.
Oh, okay. Because the total momentum before is 0, Newton says, let's write over here, P before, this is the rule of the universe, equals P after. I should say total, right? So I should say total P before gotta equal the total P after. And thank you for that, Sadia. It is actually 2.45 meters per second. Okay? Well, because the rule of the universe is right here, is that in all interactions, the total momentum before has to equal the total momentum after. And as soon as we found the total momentum before, then we know that the total momentum after have to be the same value. The prior one?
6 and 3.
Yeah. So we said the total momentum before is 18, but meters per second. Didn't you also say that the total momentum after is 18? Right. This is the foundation of this topic of collisions and interactions. The total momentum before. Actually. Well, but hold on. The combined mass. The combined mass is 8 kg, right? Oh, well, I wrote the wrong thing. Oh, sorry, 4.25, excuse me. 4.25, sorry about that. Nice catch. 4.25 meters per second.